Good morning, my students. I hope this video finds you very well on this Thursday morning. It's a very exciting time because you're about to learn kind of the next level of what you can do with polynomials. That's right. We have been adding, subtracting, and multiplying polynomials for some while now, ever since we started this unit. You guys have gotten quite good at it with your ALEKS results and what we've been doing in class, and even that polynomial floor plan project I've been seeing you work on so diligently all week. You noticed that project was a lot of multiplication and a lot of addition. So you must be pretty good at it now, and I believe that you are, which means that you are ready to begin polynomial factoring. And there's multiple ways of doing this, and we're going to learn the first way of factoring a polynomial today, called factoring by GCF, greatest common factor. That's right. And as you work on this, and if you need more practice after this video, you've got your textbook, you've got virtual nerd links, IXL, Khan Academy links. All those are designed to help you. Okay, so let's get into this. This is, again, very exciting. I'm very, very happy and very honored to be the first person to be teaching this to you. Factoring is something that you will be using often as you take not only this algebra class and finish up the year with it, but also your future algebra classes in high school and perhaps beyond. So this is a very important skill to know. So let's begin. All right, one thing that we've been talking about, and we've known for a while, is something in mathematics called inverse operators. In other words, opposites. And everything in life has an opposite, okay? It's just kind of the way the balance of the universe has to be. Everything has a yin and a yang. In other words, up. Well, there's got to be an opposite to up, and of course it's down. And the opposite of open, close, right? The opposite of left, right? And the opposite of back, well, of course, front. Okay, good. Well, what about the opposite of addition? As we know, that's subtraction. And the opposite of multiplication? We know that's division. In fact, we've been using that for several years now to solve an equation. You got multiplication, you want to undo it, use division. You got subtraction, you want to undo it, use addition. And another thing that we learned is that if the opposite of squaring something, if you want to undo something that has been squared, taken to the second power, well, that's to take the square root. Yeah, exactly. So everything in math has a opposite, an inverse operator. Even polynomial multiplication. If you want to undo the polynomials that you just multiplied, in other words, let's take everything we've been learning and reverse it, that process is called factoring, and it's time to start learning that. And again, we've seen this graphic before, inverse operations. Good. Okay, so to begin understanding how to factor a polynomial, let's identify why we need to do that. We've been simplifying polynomials so far. We haven't been solving. Now remember the difference between simplifying and solving. Here on the left, I've got 2x plus 3 minus 4x. If I asked you to simplify that, let's see, what would we do? Well, we would of course look for like terms, like 2x and minus 4x. 2x minus 4x is negative 2x. And that 3 stands alone, that constant, because there's no other like terms, and we get negative 2x plus 3. And we'd be done. That's not an equation. That's an expression. I can't simplify that anymore, and I cannot, repeat, I cannot solve for x, because I don't know what x is. It doesn't tell me. And at the same time, I don't care. I'm done. However, I look over here on the right, I get 2x plus 3 minus 4x is now equal to 17. Well, I first have to simplify again the same exact terms. 2x minus 4x, negative 2x, plus 3 is equal to 17. Now that it's equal to 17, I can continue to solve for x. All right, I'm going to subtract 3 from both sides, and I get negative 2x is equal to 17 minus 3. Okay, that's 14. Divide both sides by negative 2. I'm using inverse operators here, and I get negative 7. You see, ladies and gentlemen, you got to remember, you simplify an expression. You solve an equation. Here was my expression. Here was my equation. You simplify an expression. You solve an equation. Okay, so why are we talking about this? Because when a polynomial is factored, it can actually be solved for that variable. In order to solve the polynomials, we have to first factor them. So we're going to be spending a few days learning how to factor, and then we will simply use that knowledge to take it just a little step further in order to solve the polynomial for the variable. In other words, if you had something like 8z squared plus 6z plus 1, that is a trinomial of degree 2, and it's equal to 0, and we'll talk much later about why it's important that your polynomial is equal to 0, and the instructions were solve for z. In other words, solve for the variable. You wouldn't be able to do that unless you knew how to factor that polynomial. Because, believe it or not, there are two solutions to this polynomial. Yeah, and there's z is equal to negative 1/2 and z is equal to negative 1/4. Now when I tell you that those are the solutions to that polynomial, that equation, you might be thinking to yourself, how would you have known that, Mr. Ripes? Yeah, how would you have known that? Unless you knew how to factor. You see, you would get those solutions by factoring. Factoring is the first piece in solving a polynomial. So let's begin to learn what factoring is and the very first method of factoring, because there are multiple methods, because there are multiple types of polynomials as we've been seeing. I'll talk about that a little bit later. So let's start here. Here we have an x times a 20 minus 2x times a 16 minus 2x. In other words, a monomial x times two binomials, 20 minus 2x and 16 minus 2x. And we're going to multiply these. So if I wanted to multiply, well, three polynomials, 1, 2, 3, what would I get? Well, let's start with this little x. Let's distribute it here. And then we'll distribute it here. So x times 20 is 20x. X times negative 2x, well, that's negative 2x squared. Okay, but then we still have this 16 minus 2x, of course, to contend with. So we have to, once again, distribute. So let's see here. I got 20x times 16. All right. Let's see here. What's 20x? Oh, okay, that's a big number right there. That's 320x. Then we've got also 20x times negative 2x. Let's see here, that's negative 40x squared. Okay, good. Now negative 2x squared times 16. Let's see here. Well, that would be negative, let's see, 32x squared. And finally, negative 2x squared times negative 2x. Well, let's see, negative 2 times negative 2 is positive 4, and x squared times x to the first power is x to the third power. So I've multiplied everything out using distribution, but yeah, not in standard form, so let's make sure that it is. And I probably have to simplify something. So let's simplify first. I got a negative 40x squared minus 32x squared. So those two terms both have an x squared. All right, so I got, well, the 320x, that stands alone. There's no other term with an x. Let's see here, negative 40 minus 32. Oh yeah, negative 72x squared, because it's kind of like adding them together. 4x cubed. All right, well, good, nothing more to simplify, but I do have to put it, of course, into standard form. Let's remind ourselves, this is a degree of 3, this is a degree of 2, and this is a degree of 1, because technically that's x to the first power. So let's see here, 3, 2, and 1. So it's kind of just opposite of what I have right now. I got to reverse that. 4x cubed would be first, and then negative 72x squared, and then positive, because technically that's plus 32x to the first, because that's a positive 320. There. Got it. I just multiplied those three polynomials together. 4x cubed minus 72x squared plus 320x. All right, so why are we talking about this? Well, ladies and gentlemen, in the next few classes, we're going to learn to reverse this process. In other words, we're going to start here with 4x cubed minus 72x plus 320x. And it is our job to go back to x times 20 minus 2x times 16 minus 2x. Yeah, we have to start with where we have been ending and go back to the beginning. All right, I know that sounds kind of weird, but yes, we're going to now start with that large trinomial, and we have to go back to where it started. That's called factoring. The process of rewriting a polynomial as a product, remember the word product means the answer in multiplication, the product of two or more factors is called factoring the polynomials. Okay, well, you know what? We have to remind ourselves of something. What is a factor? Because we've known that word before, long before we ever started even talking about polynomials, and long before you even entered Mr. Ripes' math class, even in 7th grade for many of you. Yeah, you've known about factors since you were at, primary school. When you first starting to multiply, factors are numbers multiplied together to calculate a product. In other words, it's the numbers you multiply together. 5 times 3 is 15. 5 and 3 are factors. 15 we know is the product, right? Product is the answer. 2 times 50 is equal to 100. We've known that for a while. 2 and 50, those are the factors that you multiply together to get 100. And by the exact same rationale, if you're multiplying x minus 5 times x plus 4, and that's equal to 0, what you're multiplying together, those are called the factors. In this case, they happen to be polynomials, binomials. X minus 5 and x plus 4 are the factors. So whatever you're multiplying together to get some sort of answer in multiplication, in other words, whatever you're multiplying together to get your product, those things, whether they're numbers or polynomials, those are called factors. And you've also known about factors this way. If I asked you to list the factors of 100, for example, well, okay, you're asking what numbers multiply together to get 100. Well, of course, every list of factors starts with the same number, 1. And every list of factors ends with the same number, the number itself, right? Because 1 times 100 gives you 100. Okay, but there's far more factors of 100 than just 1 and 100. We can take 2 and multiply it by 50. 2 times 50. Okay, so 2 and 50 are factors. We just saw that. 3? No. 3 times something. Keep in mind, factors are whole numbers. Okay, so we're not taking into consideration decimals. Not taking into consideration negative numbers. Whew. Oh, 4. 4 is the next factor because 4 times 25. Yeah. Okay, let's see here. 5 is a factor. 5 times 20 gives us 100. So 5 and 20. Let's see here. 6? No. 7? No. 8? No. 9? Certainly not. Oh, 10. Yeah. 10 is the next factor. 10 times what? Itself. 10 times 10 gives you 100. And so therefore we've kind of closed the list, haven't we? So the factors of 100, and please let me know if I forgot one, 1, 2, 4, 5, 10, 20, 25, 50, and 100. Those are the factors of 100. Factors, once again, are numbers you multiply together to get the number that you're talking about. Factors of 25, that's a much shorter list, isn't it? Okay, so every list of factors begins with 1, and of course ends with the number itself. 2, 3, 4, 5. 5 times what gives you 20? Oh, 5 times itself. So, okay, so we're not going to have to list it twice in our list. 6, 7, 8, 9, 10, 11, 12, 13, 14. I think that's it, right? 1, 5, and 25 are the factors of 25. So that's a much shorter list. What about factors of 19? Well, of course, we've got 1. We've got 19. Are there any other factors of 19? 2, 3, 4, 5, 6. No, remember 19's prime. So the only factors of 19 are 1 and 19, right? That's a prime number. And remember, that's what a prime number is by definition. Prime number is a number that has factors that are just 1 and itself. That's it. No other numbers are its factors. So we are factoring polynomials in the same way we just factored 100 or 25 or 19. Yes, we just factored 100. We just factored 25. We just factored 19. Well, now we're not going to factor integers. We're going to factor entire polynomials. So if you're asked to factor 2x squared minus 5x minus 3, the answer to that would be 2x plus 1 and x minus 3. Because you are reversing multiplication. In this case, you're reversing multiplication of polynomials. Because check this out. 2x times x is 2x squared. 2x times 3 is negative 6x. 1 times x, positive 1x. 1 times negative 3, negative 3. But we got to simplify the like terms such as negative 6x and positive 1x. So we get 2x squared minus 6x plus 1. Oh yeah, that's negative 5x minus 3. You see? And that's where it started. Factoring a polynomial means go back to its beginning. Now, of course, this type of polynomial, 2x squared minus 5x minus 3, we're not ready to factor something like that just yet. But you see that factoring it means you're bringing it back to the two polynomials that you multiply together to get it. Here's how I want you to think about it, okay? Factoring polynomials means to rewrite the polynomial as a product of smaller polynomials. Yes. Think of it this way. Think of it as chopping wood, okay? When you chop wood, you're dealing with a large piece of wood, right? You're starting with a very large piece of wood, and you're literally cutting it up into smaller pieces. Now, each of those smaller pieces that you're cutting up the larger piece into is still wood, right? You're starting with a large piece of wood, and you're chopping it up into smaller pieces of wood. So while the big piece and the small chopped up pieces are all still wood, this is kind of like factoring a polynomial. Think of it as this. Your large piece is the polynomial you start off with. You're going to take that large polynomial and you're going to chop it up into smaller polynomials. Those smaller polynomials are called factors. The large polynomial is a polynomial, and the smaller factors you're chopping it up into are still polynomials. So I hope you're seeing the analogy here. The large piece of wood gets chopped up into smaller pieces of wood. The large polynomial gets chopped up into smaller pieces of polynomials. Those smaller pieces of polynomials are called factors, okay? But in the end, they're all polynomials. In the end, they're all wood, no matter what size they happen to be. So let's start to do this, okay? Remember this. This is so important. This is the big one. Factoring is the distributive property in reverse. There's a reason we've been talking about the distributive property for so long. There's a very good reason that Mr. Epps hasn't shut up about that distributive property since what, 7th grade? And you've been learning about it probably since 6th grade? We're now going to reverse the process of the distributive property. And to do that, we have to find the GCF, the greatest common factor, right? GCF? Don't forget that means greatest common factor. And we'll be doing that not just of numbers, but also of variables with their exponents. G, C, F, greatest common factor. All right, so let's get to our first example, ladies and gentlemen. We've come all this way. We have to factor the GCF. And our polynomial that we have to factor the GCF of is 16x plus 40. Ooh, that's a good one to start with. 16x plus 40, a binomial that we're going to chop up into smaller polynomials. Again, think of it as reversing the distributive property. And always take it in steps, like those exponent properties. Remember, we did not just look at the whole thing and know the answer. We took it in pieces. We took it piece by piece. And then we looked at all the pieces together and had our solution. Same thing here. And consider calculating the GCF of the numbers first. Then take the GCF of the variables. Let's do this first one and a few others like it together. All right, here we go. 16x plus 40. Consider the numbers first. Forget the x. Look at 16 and look at 40. What's the greatest common factor between 16 and 40? Well, a 2 goes into 16 and 40, but I think we can go higher than that. A 4 goes into 16 and 40, but I think we can go greater than that. Remember, we're looking for the greatest common factor, while 2 and 4 are common factors. It's most certainly not the greatest common factor. What number right now are you probably like thinking in your head or saying, Mr. Ripes, get on with it, the GCF is this? If you're saying 8, nice job. Yeah, the GCF of 16 and 40 is 8, right? Because 8 times 2 gives you 16, and 8 times 5 gives you 40, all right? So that GCF of 16 and 40, we're going to pull out because we're reversing the distributive property. So outside our set of parentheses, I need a number 8. I am yanking out an 8 from a 16x and a 40, specifically from the 16 and the 40. Now, I'm ready to fill in my parentheses. If I were to go back to 16x, in other words, I want to take 8 and I want to distribute it into something right here so that I get back to 16x. What would that be? 8 times what gets me back to 16x? Well, as we were saying earlier, 8 times 2 gives you 16, but I'm not just trying to get back to only a 16. I'm trying to get back to a 16x, as you can see. So 8 times 2x goes into that first slot in the parentheses. Now, what about the 40? Same idea. I want to go back to where I started. I want to get back to 16x plus 40 in my mind. So if I were to distribute 8 to whatever is right there so that it gets back to 40, what would it be? In other words, 8 times what gets me back to 40? Now, you're probably shouting in your head, 5. You'd be right. You just factored your first polynomial. 16x plus 40 factored is 8, and then in parentheses 2x plus 5. You're done. You just factored it. We reversed the distributive property. And if you want to check your work, use the normal distributive property. Okay, so let me say something before I do that. This is the answer, okay? You just factored it. If you want to check your work, distribute 8. 8 times 2x, 16x. 8 times 5, 40. Ah, good. You see? If I were to distribute that 8, I'd get back to where I started. So therefore, the proper factoring of 16x plus 40 is 8 times 2x plus 5. Now, of course, this is our first example, and you might have several questions. Let's do more examples. Let's do these 4 down here. Let's do them together, okay? The rules are, well, I shouldn't say the rules, but the steps. Find the GCF of the numbers first, then the GCF of the variables. Now, in that previous example, we didn't see too many variables. We just saw that one little x. But as you can see in these examples we're about to do, we got some more x's and y's to contend with. No worries, we got this. Find the GCF of the numbers, then find the GCF of the variables. In other words, you're taking that power of a product property and you're also reversing it. So it's not just the reverse of the distributive property, it's also reverse of that power of a product property. Okay, we got this. 6x squared minus 30x cubed. All right, well, we just said take it the numbers first, okay? Look at the 6 and look at the 30 first. Now, the way I always like to start factoring, all right, is first I open up a set of empty parentheses, just the left parentheses and the right parentheses. And whatever I factor out of my terms, it's going to go right here in front of the parentheses. Because remember, we're trying to reverse the distributive property. So let's see here, 6 and 30. 6 and 30. 6 and 30. The greatest common factor between 6 and 30. Well, we got 1, but that's not going to take us much anywhere. 2 is a factor of 6 and 30, but I think we can go higher. 3 is a factor of 6 and 30, but is it the greatest factor? Oh, you know what it is? Yeah, it's 6 itself. So I'm going to pull out a 6 in front of the parentheses because I know that's the factor, the greatest common factor between 6 and 30. All right, good. So those are the numbers. Now, let's consider the greatest common factor of the variables. We got an x squared and an x cubed. Okay, this one's going to take a little bit of thought here. Here's how I want you to think of it, okay? This x squared, isn't that technically there's two x's right there? That's x times x. And this x cubed, we know that's x times x times x. Always look for the smaller one. Guys, in x cubed, is there at least two x's? Yeah, there's at least two x's right here and here. And in x squared, are there at least two x's? Yeah, right here and here. So the greatest common factor between x squared and x cubed, in this case, would be x squared itself. Because at the very, very minimum, between x squared and x cubed, there's at least x squared in both of them. Is there an x squared somewhere contained in x squared? Well, of course. Is there an x squared somewhere contained in x cubed? Of course there is. So between 6x squared minus 30x cubed, the GCF is 6x squared itself. We took the numbers first, 6 and 30, found the GCF to be 6. We took the variable second, x squared and x cubed, and we found x squared to be the GCF. Now, for those that need a reminder, if you want to take this the long way, you absolutely can for x squared and x cubed. Check this out, guys. X squared we know is x times x. X cubed is x times x times x. You might recall from last year, to find the GCF, you have to find the matching pairs. Okay, we got a pair of x's, we got another pair of x's. So, we pull out one pair of x, we pull out another x from that second pair, and the GCF is x squared. This little x that stands alone, not needed in the GCF. Remember, the greatest common factor are what factors are shared amongst the terms itself. And, you know, this worked before as well, even with numbers. If we were to do this for 6 and 30, check this out. Well, let's see here. 6 is 2 times 3, right? And 30, let's see here, 30. Well, let's see here, 30, well, that's 2 and 15. You guys remember doing this? 15 is 3 and 5, and 2 is prime, and 3 is prime, and 5 prime. So 2 times 3 times 5. All right, so once again, we have to find a pair of 2's, pair of 3's. So between the pair of 2's, we call it a 2. Between the pair of 3's, we call it a 3. Multiply the greatest common factor is 6. And the greatest common factor between x squared and x cubed is x squared. So 6x squared was our GCF. Now, do you have to do that process every single time? No, that's just a reminder of how the process works. You'll notice the more practice you do with this, the more you won't have to really kind of factor it out this way. Now, the factor of the variables, that's something we need to practice. Now let's finish up factoring this particular binomial. Whatever gets filled into these parentheses right here, we have to think of it as, I want to go back to where I started. I want to go back to the 6x squared and the minus 30x cubed. So 6x squared times what will get me back to 6x squared? Well, of course, that would just be a positive 1. 6x squared times what will get you back to a minus 30x cubed? Well, let's see here. Let's take it in pieces. 6 times what gives you negative 30? Well, I believe that's negative 5. X squared times what will get you back to an x cubed? Reverse that product property of exponents. That would just be a single x, wouldn't it? Because isn't that technically x to the first? And x squared times x to the first, 2 plus 1, x to the third. There, we just factored it. And you can always check your work. Again, this is the answer. This is the factor. But to check your work, feel free to simply just go back and distribute it. 6x squared times 1, 6x squared. 6x squared times negative 5x. Well, 6 times negative 5 is negative 30, and x squared times x to the first is x cubed. You see, we got it because if we were to distribute it, we'd get back to where we started. So again, folks, the factored form is 6x squared times 1 minus 5x. And the 6x squared minus 3x minus 30x cubed below here, that's just the check of our work. All right, now, of course, we need more practice with this, especially with the variables, so let's do the next one here. 14y squared plus 21y. That's a good one right there. Okay, again, find the GCF of the numbers. Well, the numbers 14 and 21. Let's see here. 14, 21. Oh, the greatest common factor between 14 and 21, of course, 7. Right? 7 times 2 and 7 times 3. Now, y squared and y, we've got to consider the variables first. In y squared, there's 2 y's. There's a y times a y, right? And the y right here, that's just 1 y. So at the very minimum, how many y's are common in both of them? That's what you're asking yourself. At the very, 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 very basic minimum, how many y's are common in both of them? Well, that would just be 1. There's a y there, and there's a y there. So the greatest common factor between y squared and single y is y itself. And again, if you wanted, use the longer process of doing that, you could say y squared is y times y, and y is just nothing more than a y. And of course, you have a pair of y's right there, which means only one y gets pulled out, and that's your GCF. So between 14y squared and 21y, it's not just 7, it's 7y is the common factor between them. Now that we've pulled out the GCF, we have to now think of it as the distributive property. So, ladies and gentlemen, help me out here. 7y times what will get you back to 14y squared? Yes, 7y times what will get you back to 14y squared? Well, again, take it in pieces. 7 times 2 gives you 14, and y times a single y gets you y squared. Okay? 7y times what will get you back to 21y? Well, 7 times positive 3 gets you positive 21, and, well, y times nothing gets you y, right? So 7y times 3 gets you 21y. There it is. Factored. We factored out the greatest common factor, 7y. And again, if you want to check your work, 7y times 2y, 14y squared, 7y times 3, 21y. To check your work, simply distribute. And if you get back where you started, you know you got it right. Again, the green is just the check of your work. The blue, that's the answer we're looking for. That whole very, very minimum thing, when it comes to the variables, let's make sure that's clear. X squared was x times x. X cubed was x times x times x. At the very, 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 very minimum, how many x's are contained in both? Well, there's 2 here and there's 2 here. So at the minimum, they both contain 2 x's. That's how you find the GCF. You might be noticing a pattern with the variables here. All right, here we got 3x to the 6th plus x to the 4th. Well, let's see here. Okay, open up a set of parentheses. That's a great way to start. Between 3 and 8, what's the GCF? 3 and 8. Well, isn't the only GCF really just a 1? Okay, so we just pulled out a 1 there in front of the parentheses. And now to practice those variables. At the very, very minimum, how many x's are contained in both? Well, x to the 6 we know is x times x times x times x times x times x, 6 x's. And x to the 4th is 1, 2, 3, 4 x's. So at the very, very, very minimum, how many x's are contained in both? Well, there's 4 here, and at the very minimum, there's 4 right there. So x to the 4th is the GCF between x to the 6th and x to the 4th. So therefore, let's pull out not just a 1, but also an x to the 4th, because at the very minimum, x to the 4th is the common factor. Now that I've pulled out my greatest common factor, I need to fill in the parentheses. 1 times x to the 4th. What do I have to multiply that by to get me back to 3x to the 6th? Well, let's see here. 1 times what gives me 3? Well, that would be 3, right? All right, now again, think of the product property of exponents. X to the 4th times what will get me back to x to the 6th? Well, think of it this way. I have 4 x's already. How many more do I need to get x to the 6th? 2 of them. 4 plus 2 is 6, right? And if I were to multiply x to the 4th times 3x squared, I get 3x to the 6th. 4 plus 2. How many more do I need to get back to x to the 6th? Well, I had 4. I need to get to 6. Okay. I needed 2 more. 1 times x to the 4th times what will get me back to 8x to the 4th? Let's see here. Well, 1 times positive 8 gets me 8. And x to the 4th times nothing gets me x to the 4th. So all I need is just an 8 right there. And I'm done. Therefore, I just factored it. And again, in front here, do I really need this 1 right here? Well, no, not exactly. You can just write x to the 4th, of course. And I just factored it. Let's make sure it's accurate by checking our work. X to the 4th times 3x squared. Well, that would be 3x to the 4 plus 2, 6. And x to the 4th times 8, well, positive 8x to the 4th. And I got it. The green is the check of my work. If I get back to where I started, I know I got it right. This takes some practice, folks. I want you guys to notice something here amongst the variables. This is something interesting that maybe you noticed. Between x squared and x to the 3rd, the greatest common factor was x to the 2nd. Between y squared and y, the greatest common factor was y, and technically that y is to the 1st power, and so is this one. Between x to the 6th and x to the 4th, the GCF was x to the 4th. Anyone noticing something here to make finding the GCF of the variables really easy? Go ahead and shout it out. Yeah, it's always the lower exponent, right? X squared, x cubed. The GCF was x squared. Y to the 2nd, y to the 1st. The GCF was y to the 1st. It's always the smaller exponent and its variable. X to the 6th, x to the 4th. The GCF was x to the 4th. So you don't even have to think about it anymore if you know that. It's just the smaller variable every single time. Cool, that's going to help us for this one. Ooh, a trinomial. Dun, dun, dun. No worries. Just because we have 3 terms doesn't mean anything else has changed. We just have to do more of it. Focus on the numbers first. Well, of course, first let's open up a large set of parentheses here because we need 3 terms. We got an 8, we got a 20, we got a 12. What's the GCF between 8, 20, and 12? I think it's 4. Can I go higher? 5, 6, 7? No. Because I got an 8, 20, and a 12. And that 8 really kind of solidifies what the GCF is, right? Start with 8. Think of its factors. 1, 2. 2 is a factor of 8, 20, and 12. I can go higher. 3, no. 4. 4 is a factor of 8. 4 is a factor of 20. 4 is a factor of 12. All right, so now for the variables. X to the 5th, x to the 4th, and x squared. Let's use that information we were just talking about earlier. X to the 5th, x to the 4th, x squared. At the very, 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 very minimum, how many x's are contained in all 3 of those terms? Well, there's x squared here, so that's x times x. There's x to the 4th here, so that's x times x times x times x. And there's x to the 5th here, so that's x times x times x times x times the 5th and final x. At the very, 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 very minimum, there's at least 2 x's in all of them, right? That's the GCF. And once again, what we were just discussing rings true. It's always the smaller variable and its exponent. Between x to the 5th, x to the 4th, and x squared, which one's the smallest? Well, that'd be x to the 2nd. So that's the one you need. Okay, good. We factored out the GCF. Now it's time to fill in these parentheses. If I wanted to multiply 4x squared times something, and I needed to get back to x to the 5th, what would that be? Well, let's see here. 4 times 2 gives me 8, and x squared times x to the, how many more x's do I need to get back to 5? I need 3, 2x cubed. 4x squared times, let's see here, I need to get back to negative 20x to the fourth. 4 times what gets me negative 20? Well, that would be, of course, negative 5. And x squared times what gets me back to x to the fourth? I've got 2 x's already, so I need another 2 x's, because 2 plus 2 is 4. Okay, and now I need to go back to negative 12x squared, excuse me. So what do I have to multiply 4x squared by to get back to negative 12x squared? Let's see here. Well, this 4 times negative 3 gets me to negative 12, and x squared times, well, nothing else do I need because I already have x squared, right? So just negative 3. Boom, I got it. 2x cubed minus 5x squared minus 3 is everything I need in my parentheses. I just factored it. To check your work, distribute it out. Remember, the green is the check of our work. 4x squared times 2x cubed. 4 times 2 is 8. 8x squared times x cubed is x to the fifth, because remember, you're adding the exponents. 4x squared times negative 5x squared, let's see here, that's negative 20x to the fourth. And 4x squared times negative 3, negative 12x squared. Boom, I got it. The green is the check of my work. The blue is the actual factored polynomial. All right, we are doing well, and we learned a lot from just these 4 examples, especially about variables and finding the GCF. Remember, find the GCF of the numbers first, then find the GCF of the variables. Here's our last 3 examples, and I'll talk a little bit more, and then we'll end the video for the day there. What if you have 2 variables? Big deal. 10x squared, or excuse me, just 10x minus 10y. All right, start with the numbers, 10 and 10. Well, okay, not a trick question at all. Open up your set of parentheses. What's the GCF between 10 and 10? I think it's 10 itself. Yeah. Now here's something interesting. We got x and y. Those are very, very unlike terms, aren't they? 10x and 10y. So what's the GCF between x and y? Well, there really isn't one. So the only GCF I need on the outside of the parentheses is 10. 10 times what gets me back to 10x? X. 10 times what gets me back to negative 10y? I'm careful. I need a minus y, not a plus y, but a minus y. Done. When the variables are different, you just got to keep them separate, really. You just got to keep them separate. And check your work. 10 times x, 10x. 10 times minus y, negative 10y. Oh yeah, see? I got back to where I started, so therefore I know my factored form is correct. Remember, the green is the check, the blue is the answer, is the factored polynomial. So when you have 2 different variables, don't freak out, just keep them separate. 35a squared b squared minus 5ab. All right, so we got an a and a b here. Big deal. Take it in pieces. Between 35 and 5, well, first let's open up a set of parentheses here. Between 35 and 5, what's the GCF? You might be saying in your head it's 5. Very good, you'd be right. Now, don't look at the a and the b, just focus on the a's. Between a squared and a, and that technically is a to the first, and that's technically b to the first. At the very, 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 very minimum, how many a's are contained in both a squared and a? That would just be a single a, right? And between b squared and b to the first, at the very, 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 very minimum, how many b's are contained in both? Well, that would just be a single b, right? So, the GCF that I just pulled out of all of this is 5ab. And you notice how I was able to do that by first focusing on the numbers, then just the a's, then just the b's. We're taking it in pieces. Don't look at the whole thing at once. You'll get overwhelmed. Now that we have the GCF factored out, we got to get back to where we started. 5ab times what will get me back to 35a squared b squared? We'll take it in pieces again. 5 times 7 gives me 35. A times another a gets me back to a squared, and b times another b gets me back to b squared. Not bad. 5ab times what will get me back to minus 5ab? Well, 5 times what gets me back to minus 5? Well, that would just be a negative 1. And a times what will get me back to a? Nothing. B times what will get me back to b? Nothing, because I already have the a and the b. So I stop there. If I were to put another ab here, I'd be wrong, because a times a is a squared, and b times b gives you b squared. But we don't want a squared, b squared in this second term. We just want a to the first and b to the first. So you only have to keep it as minus 1 in that parentheses, because the ab here will be found in that factored out term. Check this out. Check your work. 5a times 7a, 5ab times 7ab. 5 times 7, a times a, b times b. 5ab times negative 1, negative 5ab. Again, you don't need a second set of ab's with that negative 1, because you already had it pulled out from that 5 all the way in the front. Done. The blue is the answer, the green is the check of our work. That one is completely for you to try. Pause the video now, try it, then unpause it. Let's see what you get. I got that. The only common factor between w to the fourth minus 2w cubed and just a single w, which is technically w to the first, is just a w. Again, just think of it as, okay, which is the smallest exponent with its variable? We got 4, w to the third, and w to the first. The smallest one is w to the first, because there's at least one single w contained in w to the fourth, and w to the third, and of course, w to the first. So the factor that I pulled out was w. And there was no real other number, greatest common factor, other than 1, right? Because that's 1 w to the fourth, minus 2 w to the third, and 1 w. So what's the GCF between 1, 2, and 1? Well, that would just be a 1, wouldn't it? That would just be a 1. I don't really have to put that 1 there, but if I do, it's not wrong. And then w times what will get me back to w to the fourth? Well, that's w to the third. And w times what will get me back to negative 2w cubed? Well, that's negative 2w squared, because technically that's a 1, so 1 plus 2. And w times what will get me back to just w? Well, just a positive 1. 1 times w is 1w, or just w. So there it is, folks. We just factored it. Nice job. Now, of course, ladies and gentlemen, we will be practicing factoring in all its forms, whether it's by the GCF or other methods, in great abundance over the next few classes, okay? Factoring is such an important part of mathematics, especially of algebra. We really have to hone the skill. This is not the last time we'll be seeing it. It is the first, but I promise you it's not the last. And there's multiple ways to factor, okay? So factoring out the GCF is important because it's used in other methods of factoring as well. So we're getting a lot of practice of factoring out the GCF. There's different methods of factoring, okay? This is just the first of many methods. Since there are different types of polynomials. There's monomials, binomials, trinomials. We've seen all those. But then also, not just can polynomials be classified by the number of terms, also by their degree. So a degree of 1 is linear, and we've been dealing with linear equations God knows how long. But then a degree of 2, those are called quadratics. Degree of 3, cubics. Degree of 4, quartics. Degree of 5, quintics, and it does go on from there. We'll be dealing with a lot of quadratics and a lot of cubics in the upcoming classes here. We'll be factoring those, okay? So keep something in mind. Factoring out the GCF is kind of the first level of factoring, the introductory, the entry-level method of factoring that we have to know first, because it's used in other methods of factoring as well. So brace yourself. Factoring is coming. This is the first method. Thank you for being patient throughout this video, guys. I'm going to have an open Zoom classroom open all day today, so feel free to pop in and out with your questions as you're working on your assignments and any other questions you might have, okay? Nice job, everyone. Very proud of you. Try your best. We will be practicing more of this, of course, next week as well. So if it's not 100% solidified, by the end of this video or by the end of your assignment or even by the end of the day. Don't worry, we'll have more practice with it. Just keep your questions coming and I'll be more than happy to help you out. Trust me, you will get good at this with practice. All right, guys, that's the end. Be sure to like, comment, and subscribe. Click that bell for notifications. See ya.